Hello, welcome back to another video. In this video, we're going to be taking a look at the IB Chemistry Paper 1 HL and question number 36 from the November 2018 batch. And this question is all to do with electrophilic addition. Let me just write that over here. It's called electrophilic, addition. Take that. Yeah, so it's called electrophilic addition. Now, this question is all to do with electrophilic addition. And electrophilic addition is a topic that comes up in organic chemistry in the HL part. So if you're an SL student, you don't have to know this. You won't be asked questions about this. But if you would like to know and learn more, then please feel free to stick around with us. So in this question, they're asking us, what is the major product of the reaction of HBr, which is hydrogen bromide, with but1ene. Now, I've put up these diagrams over here, which is very unlike of what I do. I never put up diagrams, or very rarely do I put up diagrams in my videos. Why I have done this is because my pen, the stylus that I use to draw my figures and explain to you, it's actually spoiled, which is the reason why I actually skipped my video a few days ago. And the battery that I use for the stylus, I can't find it. So I have to get a new one, and that's going to take time. So instead of waiting around and not putting up a video, I've decided to use these diagrams, which I found in the very helpful chemistry Cambridge textbook, which you can also use, and it is available on my Google Drive for free. So please check that out. But I've taken these diagrams from there, and it'll help me to explain the whole process of electrophilic addition. But before we get into what electrophilic addition is, I want to first define what an electrophile is. What is an electrophile? Now, a very similar, if you can tell by the name, an electrophile is nothing but an electron deficient species, aka a positively charged ion or the positive end of a dipole. And this is attracted to regions of heavily electron dense areas. And then this electrophile accepts a pair of electrons from this highly dense electron region to form a covalent bond. And electrophiles can also be defined as Lewis acids, if that makes sense. So Lewis acids accept pairs of electrons, and electrophiles are like Lewis acids. They also accept pairs of electrons. So typically, you'll find an electrophile has a positive charge. It is electron deficient. It needs electrons, right? So that is an electrophile for you. And these electrophiles are attracted to regions of high electron density. So for example, you have over here, this is a good example of an electrophile. So you have hydrogen bromide. So it's the exact same chemical that we are asked about in our question. So we have hydrogen bromide. Now we all know that hydrogen bromide is a very polar substance, right? Because bromine has a high electronegativity, and hydrogen's electronegativity is not as high as that. So it's polar, which gives bromine a partial negative charge and hydrogen a partial positive charge. So the dipole is going towards bromine. So there's a slight negative charge around bromine and a slight positive charge around hydrogen. And in this case, our hydrogen can actually act as an electrophile. And that is because our definition for an electrophile is that an electrophile is an electron deficient species. And clearly in this, hydrogen is an electron deficient species because it has a slightly positive charge, which is the result of this polar molecule, the polar bond, right? Bromine has a high electronegativity, so it pulls the electrons in the bonds towards itself, which gives it a slight negative charge. And hydrogen, on the other hand, isn't as strong, so it doesn't really have a choice. It gets a slight positive charge. So this hydrogen, it's pretty upset. It wants electrons. It needs to balance out its charges. So it is approached by this molecule, and this is ethene, if you can tell. And ethene has a double bond. And as we know, double bonds are made up of 4 electrons, right? Each bond is made up of 2 electrons. So a double bond, which has 2 bonds, will be made up of 4 electrons. And wow, 4 electrons in one region, that's pretty densely packed. So there is this nice little electron haven going on over here. And this hydrogen bromide, this hydrogen in the hydrogen bromide, which has this partial positive charge, it likes this, this electron haven is calling it out. It's like, come on, hydrogen, come to me. I'll give you the electrons that you want, if that helps you remember it. So this hydrogen, what it naturally does is it's going to break up with bromine. It's going to say, bromine, I don't want to be with you anymore. So it breaks up with bromine. So this arrow, this fish hook arrow indicates bromine taking the electron that it contributed to this covalent bond. And because it gets a bit angry with hydrogen, it also takes the electron that hydrogen contributed to the bond. So it takes basically both electrons in the bond and it goes away. But hydrogen is okay with that because this electron haven, these 4 electrons over here, hydrogen can take electrons from them to, well, satisfy its electron needs, if that makes sense. Now, remember, in exams, many times you're going to be asked to draw this reaction, and IB is very, very particular about the arrows, how you draw the arrows, which direction are they going in, where are they coming from. So please remember, in an electrophilic reaction, the arrow should be coming from the double bond towards the hydrogen, not the other way around. Not from the hydrogen to the double bond, from the double bond to the hydrogen. And please do not make the mistake of drawing the arrow from either one of the carbon atoms. That is wrong. The electrophilic region, the electron density region is not the carbons. It is this double bond over here. This double bond is what's going to form or contribute or donate a pair of electrons to this hydrogen to bond with it, not the carbons. So please make sure of that. Make sure you remember that. And do not forget to draw this fish hook arrow, this half arrow. This indicates a heterolytic fission. That's the fancy term for it. A heterolytic fission is nothing but a uneven splitting of electrons in a covalent bond. So basically, bromine takes both electrons from the bond and leaves hydrogen with nothing. It practically steals hydrogen's electron as well. That's called a heterolytic fission. And conversely, a splitting where both atoms take their individual electrons and leave is called homolytic fission. That is just some extra information if you needed to know. I'm so sorry I'm unable to draw. If it's confusing, I'm incredibly sorry, but I really don't have a choice. I shall hopefully get my pen repaired soon, and then I'll be back to drawing things like I usually would. So this is a case of heterolytic fission. This bromine is going to take both electrons from this covalent bond and go away. And this hydrogen is going to go and join with the ethene, my bad. Now, once it goes and joins with ethene, we are going to have a case like this, where hydrogen has gone and joined with ethene. But now remember, ethene needs to also give 2 electrons to hydrogen if it wants to form a bond with it, right? So when it takes 2 electrons out of this double bond over here and gives it to hydrogen, naturally this carbon is not going to be very happy. It's going to say, hey, we had an agreement. You just broke the deal to go with another hydrogen. Why would you do that? So this hydrogen is going to have a slight positive charge over here. Now this carbon has a slight positive charge over here, which is indicated by this positive sign in a circle. This carbon is going to be called a carbocation. So it is positive. It has a slight positive. It is a slight positive charge on it because the electrons from this double bond are taken away to help hydrogen bond with the carbon, if that makes sense. So now this positive charge over here is going to attract the bromine that left earlier. Remember the bromine that broke away from hydrogen, that got upset and took both electrons? So this bromine now, it has a pair of electrons. It has a negative charge on it. So this negative charge, this bromine, which has too many electrons, is looking for someone to share these electrons with. And well, what do you know? You have a perfect match over here. You have this carbocation who has been cheated by his partner, this partner has taken away the electrons that they had a deal upon to give to hydrogen. And now bromine is like, okay, I sympathize with you. How about I come and I give you my pair of electrons and we can bond? And carbon says, that's all right, completely fine. And this positive charge allows them to do that. This positive charge attracts the bromine, the bromide ion, which is, it has a negative charge on it, to come and bond with this carbocation. And this, what happens now, you formed a completely new compound, and this is a stable compound. This compound is not energetically stable at all. And that is because of this positive charge. This makes it unstable. So it needs to become stable again. And remember, positive and negative cancel out each other. That brings stability. So this bromine is going to go form a bond with this carbon, which has a positive charge. And positive and negative opposites attract each other. And they're going to form this bond. And now you have a new compound. And this compound is going to be called bromoethane. Sorry, bromoethane. My apologies, bromoethane. So there you have it. That is electrophilic addition. And why is it called an electrophilic addition? Is because we're adding something, right? We're adding something to this propene molecule over here. So ethene, I don't know what's wrong with me today. I can't name my organic compounds. We are adding this electrophile, which is hydrogen, this hydrogen which has slightly positive charge, and we're adding it to this ethene molecule. And then we add the bromine as a consequence as well. That is a secondary consequence. You could think of it like that. So we are adding something. It's called electrophilic addition. So there you have it. That is really the basis of electrophilic addition. Now, what is this major product? What is this minor product? What does this mean? Now, major and minor product is something that happens in this reaction over here. It's the exact same thing as this reaction, but this time we actually have a different organic molecule reacting with this. This time we have propene reacting with hydrogen bromide. And this is where the dilemma starts. This is where we begin to see what a major and minor product is. Now, if you recall earlier, I told you how hydrogen breaks away from its bromine partner and it goes and joins this carbon. Now, if you were a bit observant, you might have said, okay, which carbon will it join to? Will it join to this carbon or this carbon? That's the question I thought of first. And then I kind of realized that, oh, well, that's kind of a stupid question, isn't it? Because how does it matter if it attaches to either carbons? Both of them are the same. But it actually wasn't a stupid question. And many people who are watching this, if you thought of that, then it's not a stupid question. It's a very intelligent question. And now we get to why it matters. In this hydrogen, in this reaction over here with ethene, hydrogen didn't really have a choice. It could go to either this one. So it did have a choice. It could go to this one or this one. It doesn't matter, right? Whichever you go to, it's the same thing. Both carbons are identical. They both have two hydrogens attached to them, and there's nothing more. That's it. It's the same. However, when you deal with molecules like propene or even butene, which have more than two carbons or more than two carbons, you have a choice now. And these choices are distinct from one another. In this case, if hydrogen chooses to go and attach with carbon number 1, this carbon over here, if it chooses to go and attach with this carbon, then this carbon number 2 is going to have a positive charge on it. And remember, this positive charge makes it unstable, makes the compound unstable. However, if hydrogen chooses to go and bond with carbon number 2, then carbon number 1 will have the positive charge, and again, it's going to be unstable. But remember, reactions tend to happen in the way which gives you products which are most stable. That is what the general kind of rule is, what I have seen. So this hydrogen is going to go and bond with one of these carbons, carbon number 1 or 2. But which one it bonds with is the crucial difference. That is what allows us to have two different types of products when reactions like this happen. So as you can see, according to this graph, we have two options. We have the minor product, which is 1-bromopropane, where hydrogen has gone and bonded with carbon number 2. And we have the major product, which is 2-bromopropane, where hydrogen has chosen to go and bond with carbon number 1. And why does this happen? Why is one the minor product and why is one the major product? Why? What is the whole deal behind this? Now I'm going to tell you why. there is this law in chemistry. It's called Markovnikov's law. I'm not sure if you've heard of it. A bit complex to pronounce, but what Markovnikov's law states is that those who have shall get more, in very simple terms. In more scientific term, Markovnikov's law states that when hydrogen atom has to be added to such a product, it has to be added to a double bond, hydrogen will choose to attach to the carbon which already has a higher number of hydrogens. So now if we go by that law, Markovnikov's law, which carbon atom out of carbon number 1 and carbon number 2, which should hydrogen attach to? Well, Markovnikov's law says that hydrogen has to attach to the carbon which already has more hydrogens. And in this case, carbon number 1 has more hydrogens. So it should go and attach to carbon number 1. And then bromine will go and attach to carbon number 2. And that's why we see that the major product of this reaction will be this, where hydrogen has gone and it has chosen to attach to carbon number 1. So it follows Markovnikov's law. And the minor product, which rarely happens, is this, where hydrogen has gone and chosen to attach to carbon number 2. But just simply knowing Markovnikov's law is not enough. You have to really understand why this happened. What is the science behind it? What is the purpose? Now we come back to my earlier topic about the stability. I told you how this positive charge makes the whole molecule unstable, right? And in this case, in this reaction, it is the exact same thing. If hydrogen chooses to go and attach to carbon number 1, then carbon number 2 is going to have that positive charge. And this positive charge on carbon number 2 will make this molecule more stable than if the positive charge was on carbon number 1. And the positive charge on carbon number 1 will come if this hydrogen chooses to go and attach to carbon number 2. But why? Why is the positive charge on carbon number 2 more stable than the positive charge on carbon number 1? And this is another type of effect in chemistry. This is called the electron releasing effect of alkyl groups, or you might know it as the positive inductive effect. Both of these things are the same. And that basically means, in very simple terms, when the positive charge is on carbon number 2, these two carbons on either side of carbon number 2, they distribute this positive charge. They help to keep carbon number 2 stable. These two carbons on each side, you could think of it like tent pegs. So these two carbons act like tent pegs and they keep this carbon, you can think of this as the tent, they keep it from flying away or becoming unstable. That is an analogy that I've come up with. Hopefully it makes sense. So the alkyl groups, these two carbon groups on either side of carbon number 2, and this carbon number 2 will be called the carbocation, if you remember. This positive charge makes as a carbocation. So these two carbon groups on either side of the carbocation will reduce the positive charge on the carbon. Whereas if the positive charge was on carbon number 1 doesn't have anything over here. It doesn't have any carbon molecule or alkyl groups on this side. It only has on this side. So this makes it more unstable. Whereas in the alternate scenario, where carbon number 2 has the carbocation, this is more stable because it has carbons assisting it on both sides. That's why hydrogen, according to Markovnikov's law, to increase the stability of the whole molecule, hydrogen will choose to go and attach to the carbon which has more hydrogens, in this case, carbon number 1, leaving this carbon number 2 in the middle to develop a carbocation. But that is okay, because if the carbocation is on carbon number 2, the whole molecule will be more stable than if it was on carbon number 1. That is the difference between the major and the minor product. So the major product, in summary, is the molecule where hydrogen has chosen to obey Markovnikov's law, and it has gone and attached to the carbon with more hydrogens, because this makes the carbocation more stable. And the minor product is the one where hydrogen chooses to be a bit of a rebel, and it doesn't follow Markovnikov's law, and it chooses to go and attach to the carbon, which results in the carbocation being more unstable. So that is it. That is the difference. Now, what about in the case of the major product of the reaction of hydrogen bromine with but1-ene? So I'm going to do my best to draw. It's going to be untidy, and I'm extremely sorry for that, but hopefully you can understand. So I'm going to draw but1-ene over here. So this is what but1-ene looks like. So I'm drawing this with my hand. It's very difficult. It's quite tricky, and I know it's very untidy, so I'm very sorry for that. And I'm just going to draw these hydrogens. These lines indicate hydrogens. I won't draw it because, well, my handwriting is going to be totally messy. So this is your but1-ene, and this is your hydrogen bromide. Now this hydrogen, like I said, it's going to choose to go and attach to the carbon which has more hydrogens. And in this case, carbon number 1 has more hydrogen. It has 2, as you can see, whereas carbon number 2 has only 1 hydrogen. So hydrogen is going to go and attach to this. And then we're going to get this, this carbon over here looking something like this. I'm just going to draw it over here. I'm so sorry for drawing over this. Let me just delete this photo so that it will make it easier. Oops, I can't. Okay, anyways. Now this carbon over here is going to have the positive charge on it, right? And this bromine, which has broken away from the hydrogen bromide via heterolytic fission, it's going to have a negative charge, and it's going to go and attach itself to carbon number 2. And what we end up with is 2-bromobutane, because the bromine is on the second carbon. So it's be 2-bromobutane. So the correct answer is not 1-bromobutane, because 1-bromobutane would not be the major product. It would be the minor product. If hydrogen chose to disobey the law and attach itself to carbon number 2, then bromine would go and attach itself to carbon number 1. But they're asking for the major product, where hydrogen follows the rules and attaches to carbon number 1, and bromine also follows the rules and attaches to carbon number 2. So the correct answer is 2-bromobutane. Thank you so much for watching. I hope I have not been too confusing. It is a long, tricky concept, hard to explain in one video, but I've done my best. If you have any other questions regarding this concept or any other, please feel free to message me. I'll explain it to you privately. I will explain it to you for as many times as you need, and hopefully that should help you. Thank you so much for watching. Hopefully I'll fix my pen by the next video, and I'll see you in another video with another question. Take care, guys, and goodbye.